Hi everyone, my name is Besmira Nushi and I'm a researcher in Microsoft Research. It is a great pleasure for me to talk to the machine learning in healthcare community. So thanks to the organizers for the invite. Today I'm going to talk about some ongoing work that we are doing at Microsoft towards deploying more reliable machine learning. And this is work that is done in collaboration with multiple teams at Microsoft, as well as with our collaborators at the University of Washington. And I would like to take a chance to really thank all my collaborators in this first slide for their work and passion in this field. So in the last 10 years, we have seen multiple advances of machine learning, and we have seen machine learning being deployed in the real world. Together with these deployments and successes, we have also seen various cases of failure that have been unpleasant for the end user, or where the outcomes have not necessarily been aligned to increasing human productivity. And so the premise of this talk, which I would very much like to discuss later on with the audience in the Q&A, is that the path to deploying reliable and human-centered machine learning systems is still unpaved, and that there exist many bumps and aspects in both research and engineering that we still need to figure out. As many of you might be aware of, there have been various cases of critical failures in real-world deployments. This case here of a vision model classifying the human as a gorilla is just one example, but really one could even give a whole talk in trying to enumerate cases like this. And this is really unfortunate, but one of the things that these examples all have in common is discrepancy in performance among different population groups, or for corner cases or unexpected conditions. Now, why does this relate to healthcare, and why is this important? Well, the problem of inequality in quality of service is an open issue in healthcare. And as a machine learning community, we need to make sure that the introduction of algorithmic support and decision-making and automation does not increase and automate inequality. Here, I'm only showing one study that speaks in length about this problem, where the medical professionals emphasize that disparities represent a significant quality problem. Current data collection efforts are inadequate to identify and address disparities, and that clinical performance measures should be stratified by race, ethnicity, and socioeconomic position for public reporting. As you can see, this is a very parallel story to everything else that we are seeing today, with discrepancies and biases in machine learning models, and also for vision algorithms. Now, if we take a step back, though, in the engineering practices that we have today, we see that we have gone a long way ahead in providing IDEs and tools for traditional software development. And if you are a machine learning engineer today, there is very little support when it comes to efficient troubleshooting and debugging and performance evaluation for machine learning. In fact, just as recently as last year, we did a survey study with more than 500 machine learning engineers to ask them about the main challenges and best practices that they are following in their work. And the top issues that they raised in this study were related to infrastructure, tooling, and difficulties in debugging. Therefore, while you might be a motivated and systematic engineer, the lack of tooling doesn't make your job easier, and oftentimes you have to build a spaghetti of scripts and visualization primitives yourself and in a manual way to really understand what is going wrong with the system. To this end, I'm going to cover three topics that summarize our current efforts. First, I'm going to talk about a tool that we have built on rigorous error analysis for machine learning. Then I will switch the attention to problems related to versioning and monitoring machine learning systems. And finally, I will briefly touch upon recent efforts on rethinking machine learning properties in a human-centered way. And you may notice that I will switch the attention oftentimes, depending on the stakeholder, from the machine learning practitioner to the end user and to the decision maker. So let's get started with error analysis for machine learning. And I'd like to point out that a lot of bias and performance discrepancy issues in machine learning, they really do start with data problems, but they get finally baked into deployment through poor performance reports. For example, how many times have you seen an article that claims that a particular model is 90% accurate or something like that on a given task and benchmark? And unfortunately, this is using a single score metric to describe the model performance in the whole benchmark. And parallel to this, we still also use these types of metrics in tables in research papers and competitions where the leaderboards rely on a single aggregate measure. The problem here is that single aggregate metrics make the assumption or maybe create the illusion that performance is uniform across the benchmark, and therefore they can hide important conditions of failure, while in the real world, we know that model performance can be wildly non-uniform. And the gender shade study is a great example of this. Here, the team of the authors discovered that the error rates for gender detection are much higher for women with a darker skin tone. So there is a need to think about this intersectionality of errors in the system. However, since there may exist many of these conditions of failure, from an engineer perspective, the question remains, how do I streamline the process of error identification? So therefore, the vision of our collaboration across Microsoft has been to build tools and methodologies that help engineers accelerate the development iterations by identifying errors faster, systematically, and in a more rigorous way. For doing this type of fine-grained error analysis, in 2018, we proposed an error analysis methodology called Pandora. In Pandora, we open up the box of system inputs in a benchmark, and we chop it into different semantic clusters based on the input content. And for each cluster, we build interpretable models that can describe when and how a system fails. Based on Pandora, we then built a tool that we call Tool for Error Terrain Analysis. And this tool consists of different visual models. First, the engineer runs the benchmark on the model that they want to inspect. Based on the performance of the model on each row of the data, they compute error labels for each instance. And in the simplest case, the error label will tell us whether the model has failed or succeeded in performing its task. The engineer may also decide to augment the data set with meta features that come either from crowdsourcing or from an external model or from the execution streamline of the system. And after this is all set, we build interpretable visualizations either at the global level or for a particular cluster of interest or for a given instance in order to understand where and how the system is failing. So we call this error terrain analysis because really what we're trying to do here is to understand the terrain of failure and how does that change for the different input conditions. The tool is currently being used by multiple teams internally at Microsoft, and we are working with the Azure Machine Learning team in order to open source it for the wider community. And currently, the teams that are using the tool span across different types of domains, like such as, for example, in vision for eye tracking and skeleton tracking, or for face processing, and also Windows infrastructure team is using it for tabular data. So let me show you one use case of how we use the tool for further understanding of the benchmark in the gender shade study for the task of gender detection. Now, keep in mind that the task of gender detection perhaps is not the most representative task in face processing algorithms. However, it is a good task for understanding how certain societal biases can creep into the model. Here I am showing you that the benchmark that was proposed in the gender shade study, consisting of 1,260 photos from candidates of parliaments across the world, was augmented with meta features that came from the Face Azure API. So basically, this augmentation includes features that are related to whether the person in the photo is smiling or not, related to perhaps whether they have facial hair or are wearing glasses, and other facial features. And of course, across the two dimensions of gender and skin tone, we see again that the errors for women with a darker skin tone are much higher. However, we also wanted to dig a little bit deeper and to understand the particular input conditions for which these types of failures happen. Here I'm showing you a different type of visualization in the error terrain analysis tool. And here we see that the base rate for errors is 5.5%. And then it becomes 11.5% for women. And then it becomes 23.7% if these women are not wearing eye makeup, 31% if they have short hair, and it increases up to 35.7% if on top of this they are also not smiling in the photo. And this reveals hidden conditions of failure that one cannot otherwise, extract without having the help of automated tools. And in this case, as a developer, you'd have to look at all the possible combinations of failure to be able to extract the pattern. Now, in addition to this type of visualization, we also have other controls that are related to instance visualization or to data exploration and comparison capabilities that we are hoping to be able to make open source very soon. Great. So next, I'm going to talk about an aspect of model versioning and monitoring in machine learning that we call backward compatibility. In traditional software engineering, the notion of backward compatibility is very well defined. If we have two components, A and B has a dependency on A, if component A is updated, but B stops functioning after that, we say that A is not backward compatible. In software engineering for machine learning, the problem can be a little bit more complicated than this. So basically, the data interface between the two components may remain the same, and they may still be able to communicate with each other. And B may still continue to function, but its performance may significantly decrease after A has been updated, even though A may have a higher accuracy. And the reason why this happens is because A might have introduced new errors that were not previously present before. So let me talk a little bit more about this. Going back to performance reports, as of today, we compare a baseline model with a candidate model based on this single number again. And we see that if the candidate model has a higher accuracy, it is then a better model for deployment. However, though, if we visualize errors in a different form and from a different lens, for example, if we visualize them in the form of a Venn diagram for the two models, we can quickly realize that sometimes the new model may be making new types of errors and introduce partial model regress. Ideally, though, we would like the error regions between the two models to intersect as much as possible and be able to deploy fully compatible updates. And for example, in this case, if you have two candidate models that are perhaps equally accurate, you may want to deploy the one that is more compatible. However, though, one can rightfully ask, why does this happen in machine learning? And in fact, there might be different sources of incompatibility. A lot of you may be familiar with optimization stochasticity that is introduced during optimization. either for model initialization or during data augmentation, or because you're doing distributed training. But there may exist other data issues in the new data set in the form of label noise or feature distribution shifts that cause incompatibility. And of course, fundamental architectural challenges may also cause incompatibility. Now, this concern raises the need for considering these models not just as isolated components, but also to be able to put them into an overall system perspective. And this perspective is really twofold. We want to maintain trust with a larger system, software system, and with third-party applications. And also, we want to maintain trust with human end users for HumanAI collaboration. Now, we have done some research on both of these topics, which are shown here, and this is really work that is led by our intern Gagan Bansal and also PhD student at the University of Washington, and our AI resident Megha Srivastava, who is soon to be a PhD student at Stanford University. From a software system perspective, at the heart of the problem is the problem of error handling and chain effects. Whenever a new error is introduced in the pipeline, subsequent components may not be aware of this error. So basically, the contract that existed earlier is broken. And if there existed any exception handling procedure or any training that has been done on model B so that it suppresses the errors of model A, which happens very often in practice, then these errors will flow in the system and will remain unhandled, which creates a maintenance problem. Another example is HumanAI collaboration for decision-making. For example, imagine a doctor that is using a classifier to predict whether a certain patient should be released or not, or whether they should be put in a special outpatient program. And imagine you have this model that was initially 80% accurate, but the model was trustable on elderly patients and has never broken human trust for this particular data region. Now, say as a developer, you deploy another model that is 90% accurate, and you think that this is a much better model, but this model is going to break human trust and perhaps mislead the human to take the wrong decision in certain errors. So the problem here is that the error boundary of the update is very different from its previous self. So the main message from this discussion is that improving accuracy is not the only metric that we should care about, and especially when the model is put into a system perspective. Here, we propose to look at compatibility scores along with accuracy scores. And the definition is very simple. Basically, we're looking at out of the cases where the model was right, how many of these decisions remain to be correct even after the update. So going back to the previous example, say you have two candidate models, the upper one and the lower one in this slide, and they are equally accurate. The lower one is more preferable to be deployed because it is more compatible to its previous self. So basically, it is just trying to refine the error boundary of the previous model without introducing new errors. Now, we did some experiments on data sets on high-stake decision-making, and we see that with raw updates that do not take into account compatibility, we can see that often compatibility can be as low as 40%, for example, in this case, for the mortality prediction task, which means that out of the cases where the first model was right, 60% of them are now going to be wrong. What can we do? So we propose to use a reformulated loss function that takes into account, together with the traditional loss function definition, takes into account dissonance. And dissonance in this case defines the disagreement between the two models. Now, we had various definitions of dissonance in the paper, but the one that works best for our use cases was the new error dissonance, which basically is adding an additional loss to every case where the initial model was correct. Here is an example of the exploration graphs that we are showing. In the x-axis, we show the compatibility score, and in the y-axis, the performance, in this case, AUC score for the mortality prediction task. And we can see that if we consider each dot in this graph as a different model, there is a freedom for the developer to pick a model in an informed way so that they can be able to maintain accuracy and still increase compatibility up to a certain extent. In this case, up to close to 0.67 compatibility score, which is much higher if you compare it to the initial compatibility score. However, though, we can still see that this is a trade-off, and there is the question of what can we do beyond the trade-off? Like, how can we support this better? And in a recent work that is coming up in KDD, we show that the distribution of the incompatible examples themselves may be a useful guide for pinpointing where the data issues are. For example, here we have introduced label noise in the CIFAR dataset between cars and trucks, and we see that these classes are also the ones that are most affected by incompatibility. And the hope is that this type of analysis can then become an additional mechanism in our toolkit for going back to guided data repair. So let's move on to our next section related to human-centered properties of machine learning. Earlier, I briefly touched upon the topic of HumanAI collaboration, and I mentioned that compatibility is a good property for maintaining trust in human AI teams. This brought up a lot more questions in the work that we are doing together with the University of Washington on thinking beyond accuracy and trying to understand how can we optimize machine learning models for collaboration, and what are these properties that a good AI collaborator should have. For example, in a human study that we conducted in an abstract gamified domain, we show that the geometry of error boundaries matters for collaboration, in that if we expect the human to take over and override the machine when the machine is wrong, it is easier to do so for the human if the machine learning error boundary is parsimonious, non-stochastic, and compatible over time. And we are doing ongoing work here to ensure these human-centered properties during machine learning optimization. Now, the next question that came up was related to the fact, well, can explainability help people to take over the machine when the machine is wrong? So basically building justified trust. And so we ran more studies in 3 different NLP domains where we asked workers on mechanical Turk to collaborate with a machine learning model that sometimes would only show its prediction and confidence, but in other conditions, it would also show different types of state-of-the-art explainability techniques that were explainability techniques based on feature attribution. And we found out that team performance, humans and machine together, does not improve over the confidence-only condition, and that explanations can even mislead people to take the wrong decision. And such results raise an open problem on how do we enrich our set of interpretability tools so that they support human and AI complementarity and help with handing over control at the right time. Now, finally, I also want to point out the important caveat here that these studies have been conducted in the lab or in the form of games or mechanical Turk experiments. But in order to really address this problem, we will need, as a field, large-scale experimental studies on high-stake domains, together with decision-making professionals. And I'd like to take the chance to invite everyone who is interested in organizing such studies to reach out and see how can we work together so that we can understand collaboration where it really helps, where it is really happening out there in the field. So to conclude, I hope I was able to bring some attention to the fact that we still have a lot to do to pave the way of deploying reliable and human-centered machine learning, and that providing better tooling and designing for human-machine collaboration are perhaps two starting points in this path. Thanks again, and I'm looking forward to your questions.